We have on DT26HP machine fixation points, holders which are mounted on fixation points, and tools assembled on holders. I will use as synonyms the following terms: fixation points and attachment points, and holders and articles. Each of these elements has its own geometry. First, let's start with tool holders. This configuration of holders to machine our sample parts isn't the only possible one. It has two optional holders. The first one is B-axis with rotating tools. This equipment reduces the available space on gang 1 to assemble the other holders. It locks some fixation points. That is why we have on a machine 3 not for live holders and a holder for stationary cutting tools of cross-section 12 by 12. There are 5 possible tools to assemble and not 6. The other optional equipment is double stationary holder in back operation. This table presents all available holders to a mount on DT26HP machine. This table is contained in Tornos documentation titled Maintenance and Use. This list of available holders is also contained in TISIS. Each holder has as attribute unique identifier and the list of fixation points where we can assemble a given holder. The correction of holder configuration is validated in TISIS and also checked on a machine. When we mount a given holder on a selected fixation point, we call this point reference attachment point, and holder geometry is determined according to this point. The description of all holders' geometry we can find in the same documentation, Maintenance and Use, but it is also involved in TISIS package. TISIS software involves a special program dedicated to holder and tool geometries. It is Article Editor. Let's open this Article Editor and first select the type of our machine. Next step is selection of identifier of our holder in this list of all available holders. This is our holder, and in this form general information on it is grouped. Now we should select a reference attachment point for our holder. On our machine with B-axis, the only possible such a point is fixation point 13. And now on the right side of the screen you see the description of holder and all slots of this holder. You see that each tool which can be assembled on this holder is identified by its number. So first, before consideration of holder geometry, let's discuss how to create tool numbers. The principle to create tool number is very simple. First, it is character T, like tool, followed by 3 digits. The first 2 digits are number of reference attachment point, and the last 3rd digit, this is number of a tool position within a holder starting from 0. Next character is D, followed by 1 digit of value 0 to 9. This is number of tool geometry. This construction with D character we use when we would like to define more than one tool geometry, for instance, like for grooving tool. Knowing this principle, please look how tools in this drawing are numbered. First, for this holder for stationary tools, we have attachment point in PF13. That is why tool numbers are T13 0, T13 1, and so on. Next holder, this is leaf holder. It can secure only one tool. That is why this third digit is always 0. And then we have number T14 0, T15 0, and so on. This rule of tools numbering applies also to tools from B-axis. Reference attachment point for B-axis is PF30. That is why we have tools with numbers T30 0, T30 1, and so on. Let's discuss now holders geometry, starting from x-axis. Please look into this kinematic drawing showing x and y axis. You see here the value 34. This is the distance measured from reference attachment point for this holder, this is PF13, and the edge of a holder. This is the edge of a holder. And this is value 34. Please look that x-axis is, of course, diameter axis, so this value 68 is the value of holder geometry in x-axis because it is 34 multiplied by 2. This value 68 is common geometry for all slots of this holder. And what is geometry in y-axis? You can notice here that this is the distance between this reference attachment point to the ground surface of a slot. This is ground surface of a slot. It means that this value of geometry will be different for each slot. The values you can find here at the bottom of the drawing. And we can compare with editor article that they are exactly the same in the editor. We can deal now with tool geometries and start as previously with x-axis. Please look at this value 20. This is the distance between edge of a holder and tip of a tool. It means edge of a holder and tip of a tool. And this distance is 20. It corresponds with value 40 as geometry of a tool in x-axis. Let us now deal with y. Y is connected this value 12, and it is the distance between this ground surface of a slot and tip of a tool. In standard case, it is just width of this insert holder, which equals 12. It means that in standard, all geometries in y-axis are the same and equal 12, as you see in article editor. Tool geometries of values like in the kinematic drawing are called standard or default tool geometries. Let's discuss now leaf holder geometry. You see here the value 10, and it is the distance between reference attachment point and the edge of a holder. This value 10 corresponds with value 20 given by diameter as holder geometry in x-axis. Tool length is also defined. This is in standard, this value 44. This is the distance measured from holder edge to the tip of a tool. And of course, it corresponds with this value 88, which is tool geometry in x-axis. In both cases, tool geometry and holder geometry in y-axis, the value is 0. We don't see here z-axis, so we cannot discuss it now, but I'd like to add a short comment concerning b-axis. You see the details on it in this drawing at the bottom. And first, this is the range of movement of b-axis shown, starting from plus 90 degrees to minus 45, altogether gives the range 135. Reference position of b-axis is radial position, it means this is plus 90 degrees. The standard length of tools assembled on b-axis you can also find in this drawing. First, they are measured in the same way as the other tool lengths. It means that this is the distance from holder edge to the tip of a tool. And it applies both to main operation and back operation. Standard tool length is bigger in main operation because it equals 50.2. In back operation it is shorter, equals 35. Let's discuss now holder and tool geometry in z-axis. First, please notice in this drawing this symbol. It depicts reference point for geometry definition in z-axis. When we follow along this line, we'll see that this is cutting line. It means that it is line which goes at the bottom of all slots. This is slots and this is bottom of a slot here. Distance between this cutting line and machine 0 is 21. Taking into account direction of z-axis, we receive the value minus 21 as geometry of this holder in z-axis. This value is the same for all slots in this holder. If a tool is mounted that way that tool tip goes in one line with the bottom of a slot, then standard tool geometry in z-axis is 0 for all tools mounted on this holder. This is main operation, and now shortly discuss back operation. First remark is that the rule to number tools is exactly the same as we said previously. Please notice those tools, they are stationary tools, and these are stationary holders which can secure only one tool each of them. That is why the last digit is always 0. The first two, they are number of fixation point to assemble a holder. And here at the bottom, the standard length of a tool is given. It is measured from the edge of a holder to a tip of a tool. We can discuss now geometry in z-axis of leaf holders. First, main operation. Please look that the distance between center of a tool and machine 0, this is 28. Taking into account z-axis direction, we have geometry minus 28. And the same value we have in article editor as geometry in z-axis. Please notice that the distance between cutting line and center of a tool is 7 mm. In back operation, in our configuration of machine, we use leaf holder at this position 54, and information on geometry of this holder and tool assembled is shown in this small drawing. We can say that Definition of geometry in TISIS and on a machine is hierarchical. What does it mean? It means that we have 4 levels of this definition. The first one is geometry of fixation points. It is measured by tornos and stored in TISIS and on a machine, and there is nothing to change in it. The second level, there are holders geometry. They are also measured by tornos, and those dimensions are stored in TISIS and on a machine. A user has nothing to do with those 2 levels of geometry, but he or she is responsible for the next 2 levels. Tools geometry. Standard values are suggested by TISIS, but it is a user responsibility to measure the real values and enter them. And the last level, wares, are also defined by a user during machining.